You have this kind of interaction between solid and fluid to define the multi-body system. Everyone who did this in a finite volume CFD, we have tools how mesh is behaving, but it's never really native in these particle applications like shonDye. You get this multi-body interactions in a native way. What we have to add at the end is also the reference frame, because the wiper has to move with the motor. We will put the reference frame.
All right, ladies and gentlemen, welcome to another deep dive session together again with shonDynamics and Moritz Schenk. Today it's all about exterior water management. Exterior water management is a key discipline in vehicle development, directly impacting driver visibility and therefore functional safety. As development cycles shorten and physical testing is reduced, accurate virtual simulation of water behavior on vehicle surfaces become increasingly critical. Yet, exterior water management simulation remains technically challenging on several fronts. Number one, coupling the aerodynamic flow field with water transport. Number two, multi-body interaction, such as the dynamic motion of windshield wipers. And number three, defining a physically representative rain model or other ways to approach the engineering problem. The livestream will give a quick walkthrough of these challenges and how they can be approached with the tools from shonDynamics, mainly shonDye, by setting up an example simulation of a windshield wiper case with an imported external flow field around the car model. With that out of the way, I'll hand over to Moritz. Moritz, the stage is yours.
Okay, thanks, Yusuf, for your kind introduction, and also thank you for having me again. Also, welcome from my side. As Yusuf already said, in today's deep dive, we will talk about mainly exterior water management, and the example application will be the A-pillar overflow. Before we go directly to our software and to our example case, I shortly want to introduce who we are, because I think Yusuf has a large community and not everyone will know us. So we are shonDynamics. We were founded in 2018. We are a company which develops CAE tools for engineers. 1 year later, after our founding in Karlsruhe, we also opened an office in Suzhou, China. At the moment, we are around 80 employees, and from these 80 people, around 50% are developers, which are distributed between our different software tools. And our customers you can find mainly in the field of the electric vehicle sector. In today's deep dive, we will talk about two of our products, shonFlow, which is our general finite volume method CFD tool, and shonDye, which is our oldest product. This is a mesh-free CFD tool, and this will be also our focus on today's deep dive. Also, we will be 80% of the time we will be in shonDye. shonDye is based on the moving particle simulation method. For those of you who are already used to particle simulations, it's a little bit compared to the SPH solver, but compared to the SPH solver, the MPS method solves one additional pressure solving step, and hence it's considered as more accurate. As additional features in shonDye, we have a fully coupled fluid to solid interactions and solid to fluid interaction, and also multi-body dynamics simulations. These two features are really important for today's application, example application there. And also, shonDye can run on GPU and CPU, and they're also on desktop PCs and HPC systems. All the cases you see today are run on my computer, and they took around, I would say, half a day to 60 hours. So when we talk about water management, we can differentiate between two approaches. One, the whole car is considered, and we have a moving car going through deeper water. So a wading scenario. If you are interested in this kind of scenario, you can watch our last deep dive from end of last year. There we focused on this kind of scenario. Today we want to have a more detailed view where we take out one part of the car and want to look how this behaves according in rain, or if it is matched with water. So what is A-pillar overflow? And why is it important? I think Yusuf already give a short introduction why it is important. So it's a safety issue. So when water goes from the windshield over the A-pillar to the side view of the passenger or driver's seat, it can block the driver's view to the mirrors and outside of the car, and therefore it's a safety issue. So it is important to handle this kind of behavior. And why is it of interest to simulate this kind of scenario? Here in this image, this is a really nice image of a publication. There's an experiment. And if you look what is needed for this kind of experiment, you need a wind tunnel, you need a defined airspeed, you need defined spray rack. There they use also UV tracer fluids and UV illumination to track the fluid. So it's really cost and time consuming to do these experiments. And therefore our customers are interested to do this kind of simulations in a really early stage of the development to get rid of design flaws and such stuff. So it's really a need to do this kind of simulations in an early stage of development. And for this kind of simulations, we want to give engineers and our customers the correct tools for it. In today's deep dive, so this is mainly the whole deep dive. We will go through it. First, we have model, and then we will set up step by step our A-pillar overflow case. As a model, we will use the already from our side well-known driver model from TU Munich because we are interested only in the windshield and side windows and the A-pillar model. We took a really simplified version of the driver model, so we don't need a bottom or also don't need any tires for it. The driver model doesn't come with wipers, so therefore we also modeled simple wiper geometries on the windshield. So this is always, let's say, a little bit of a disadvantage to be a software company. Our customers want to do their geometry or their simulations with really detailed and their own geometry, but they don't want to have the geometry shown in these public viewings. So for this kind of deep dives or advertisement material, we always need open source or own geometries to show these kind of cases. So this is not a real geometry, but a simplified version of it. But this said, I just want to be sure about it that it's a simplified version, but the workflow also works with more detailed geometry. The first step of our deep dive would be now the finite volume method simulation, where we simulate the flow field around the car. Then we will import or export, first export and then import the flow field to shonDye. There will be a one-way coupling to the fluid. So this means the airflow won't be disturbed by the fluid, but the fluid will be disturbed by the airflow around the car. Then we will set up a multi-body simulation, add a rain model to it, and then we will get our final simulation. Okay, so this is then our whole simulation or deep dive step by step. And now let's go to the different programs and go through it step by step. This said, let's go first to the shonFlow simulation. This kind of simulation, this flow field around a car, is an own deep dive by itself and an own scientific field. So I'm not an expert in this kind of simulation, but to show you the whole workflow, I did a really simplified version of this kind of simulation and want to show you how it is done. So this is now our result of the finite volume simulation. We export the whole flow field as a CSV file, and then we can directly go to shonDye and import this kind of results. In the last deep dives, I always started completely from scratch. If you want to see how a completely new case is set up, you can watch these kind of steps in earlier deep dives. But here I prepared a little bit, so it's not so repetitive. So this is our simplified driver model with wipers on the windshield. There we can import now our field. Okay, I already updated and imported the field, and yeah, this is the same field as you already saw in shonFlow. You can check if everything is worked for the import and check the different sizes. Also here you get a small overview of it, how many cells are imported and maximum and minimum velocity. So if the import works fine, then you have to set 3 different parameters. First, the ambient density. So here it's logically the density of air of the surrounding car. And then you need a reference diameter. Here I use the diameter of our particles and a drag coefficient. So the interaction between the air and the rain is considered later physically. Now I hide the display the field again. And one other thing you want to start at the beginning is to define the domain around the car. You could consider the whole domain, but this would need a lot of physical and computational time. And we are only interested in the first, or in the front part of the car. So we can reduce our domain only around, and this means also that all other cells of the domain are cutted and only these cells will be considered, and this speeds up our simulation notably. So we hide now our field, so we can work completely freely here. I set up already the movements of the wiper, of the right wiper, but want to show you how to set up the wiper movement for the left wiper. So we have to do it only once in the deep dive. So for the left wiper, we need 2 movements around this point of rotation, and also about around the wiper itself. The arm will be the active movement. So here we will add an active rotation. shonDye sets as default. It will be set in the center of mass of the geometry, but here we want to have the movement around this part. Either you know the location of the rotation, or if you don't know it, we added some helping tools to find this rotation center. Therefore, you will set the visibility of the mesh of the geometry and active a center picker. So here our goal will be to find the center of this geometry, or around of this circle. So therefore we can select different mesh points, and if we select 3 points, it will be considered as a circle, and then it will give us the center of our circle, and we can copy this point and paste it here. And now we get the rotation center directly at the spot where we want to have it. The red axis will be our rotation axis. This will be vertical to the plane here. So we also get this from our little helper. And we can also paste it here. And now we have the correct rotation center and also the correct axis where to rotate. This will be the default rotation direction. So this will be the positive direction. I know that I defined my rotation later in a different way, so I have to change the signs in front of it. So I get the right default rotation, and now it rotates in the correct direction. This is now our rotation definition of rotation. Now we want to set the motor of the periodic movement of the wiper. There we can upload also a CSV file. And then we get directly the periodic movement of the wiper. Here I choose, I think, 0.75 Hertz movement, and with a pause at the first half second of our simulation. So this means the multi-body system can settle, and also the rain can get to the windshield, and so on. So this definition is now finished. Then we need 1 second movement, the passive movement of the rubber or of the wiper. Therefore, we need a rotation log. There, the rotation center is already correct, but the red axis needs to be vertical to the wiper. Therefore, we need again our little helper to find the correct the correct plane. Here, the center is not so important. We would only need the normal direction. Copy it and put it here. Great. We wanted the left wiper. Here. This was a mistake. Left wiper. I delete it and add a new one. Add log so. And the normal direction. So now we have the correct axis of rotation, the correct position of the passive rotation, and what we have to add at the end is also the reference frame, because the wiper has to move with the motor. We will put the reference frame to the left arm. So this means that it won't change its position in reference to the wiper arm. So if the wiper arm goes up, the wiper rubber will follow. So this is our setup of the movement of the wiper. As the last point, we have to simulate or to define the interaction between the windshield and the wiper rubbers. Therefore, I switch of this view because this is not needed anymore. We need it later, but now, for now, we don't need it. And we have two options for this. We can use a mesh collision model. This is defined. This is used for the windshield because the windshield is not completely flat. It's really difficult to use primitive bodies for it. So therefore, we use the mesh as the collision body. For the wiper, we only need the two connection points at the front and at both ends of the wiper. So that it's enough to have there two connection points and two collision bodies at both ends. And therefore we need two primitive bodies, and I use the sphere model to get only two contact points. Let's rename it to left, the first one. We switch on the mesh view and also our little helper. There we know now this is the location we want to put it. Paste the vector. This will be our collision model, and this is way too large, so let's make it a little bit smaller. And if we hide everything, expect the left wiper, we define it a little bit better. So we want to have it a little bit smaller than the wiper, so the wiper sinks in a bit into the glass, so there's no gap between wiper and windshield. And I think this is for now good enough. We have to do this the same on the other side of the wiper. This is not so important to, at the end is enough. Copy it, a new model. Let's rename it right. Paste it and reduce a bit. So here you see it's a little bit too large. This would mean that there would be a small gap between wiper and windshield, and their fluid could escape. So let's make it a little bit smaller. And then it can sink in a bit and wipe properly. So this is the definition of our multi-body system. I would consider always if as soon as the multi-body system is set up, just check it if everything works fine, because now we are here in the live stream, can't wait for it. I've already calculated in advance. And here you can see, we can jump to the start. So first half second, nothing happens. So only the multi-body system settles, and then we start the rotation as we want to have it. So now we have the field definition, we have the multi-body definition, and now we need the fluid definition at the end. There I define an inlet. I switch this also off. We use for this example, we use a rain inlet in let's say 1.6 meter above the car, or not above the car, but yeah, above zero, and make it as wide as the car itself, and 1.5 meters. So this is the definition of the rain model. Then you can say how much rain you want. Let's say this 50 millimeters per minute. This is a really strong rain. So yeah, it's more or less a thunderstorm-like rain. And you can also give it an initial velocity in the direction of the red axis. And more or less, this is it. This is how you set up the correct simulation. And as last point, you can check if the domain is still small enough. This is perfect. This is what we want to have. We want to set the particle radius. This is 0.5 millimeters now. And also how long we want to have the simulation. So let's say 5 seconds, the total simulation. And this is how you set up this kind of multi-body simulation in shonDye. In the last part of our deep dive, I want to discuss a little bit about the results. So you could run now the simulation. We don't have 10 hours time for it, and I don't know what to talk 10 hours. So I also directly have the results for it of different cases. And I switch back to the presentation where we can discuss directly these kind of results. So this is again our multi-body results, and this would be now our final simulation result with different kind of post-processing options. So for the water, I used always the number density as valuable. This means the number density is a value for how many neighbors does a particle have, and this means in the other direction, so how much chunks of fluid are at one point. And on the surface, I used always the coverage rate as a variable, and their coverage rate averaged over time. So because one time step, you can't see any patterns, so it's always useful to use the time average value of this kind of value, so you get some patterns, how the fluid behaves, and so on. I want to show now you the results of these kind of simulations in a slightly different setup, but here also the rain setup at the top of the car, with different kind of fluid fields or flow fields, not fluid fields, flow fields. One is the field deactivated, so the rain comes directly straight onto the car, then with a rather slow a boundary condition of 10 meters per second flow field as a boundary condition, and 25 meters per second flow field. And yeah, as you can already see in a 10 meters per second case, the flow field or the rain is not so bended like in the 25 meters per second case. There, the rain is really bended towards the car, and we have forming of small rivulets at the side of the car. Compared to the 10 meters per second case, we don't have this kind of rivulets forming in near the A pillar and near the side window of our driver seat. And if we look now on the side window in more detail, and the averaging time of the coverage rate is 2.5 seconds, so half of our simulation. The field deactivated case is not so interesting. We see chunks of fluid are collected in top of the car and on the A pillar, and then it drops down to the side window, and we have a distribution mainly around the back of the side window. I think the more interesting cases are the 10 meters per second case and 25 meters per second case. And here we see, if we average over 2.5 seconds, that most of the fluid is at the back of the upper right corner of our side window, not so much blocking the view of the driver to the mirrors or outside. Whereas in the 25 meters per second case, we have a lot of rivulets forming at the start of the A pillar, goes to the side view, and then back to the back end of the car. If we look at moving results, or of video results of it, and average over 0.5 seconds, we also see different kind of behavior in the 25 meters, in the 10 meters per second case on the left side, and 25 meter per second case on the right side. On the left side, we see, okay, we form here the ground noise more or less, but in accordance to the movement of the wipers, we see always more and less fluid periodically on the side view of our window, whereas in the 25 meters per second case, we just have the rivulets, but they are not so dominated by the movement of the wipers. So here we can say the flow is dominated by the flow field around the car, and the wipers are more or less pushing the water directly back to the car and not to the side of the car, and compared to the slower case. So this would be one setup of our case. The next setup is, if you don't want to simulate a whole rain inlet and just want to know, okay, what happens if I just put a film inlet near the A pillars on the driver's seat and on the passenger seat, and put a lot of water there, what happens here? This simulation is much faster, and you can directly put water there. So shonDye gives you the freedom to do also this kind of cases and these kind of fast simulations, and then you can compare directly the two driver seat and passenger seat. And here you can see that also the driver seat is much more connected to the wiper movement than the passenger seat. Here you have a more or less evenly distributed flow, where on the driver's seat you have this periodic more and less fluid. So, but this is logical if we look at the setup, how the wipers are positioned and how they rotate. And as a last setup case, you could also put the rain inlet directly in front of the car. If we go back to the beginning of our deep dive and look at the experimental setup, this was their setup. They put the rain inlet or the spray inlet directly in front of the car and not on top or something like this. And this is also the reason why you can, or one of the reasons why you can put an initial velocity at the rain inlets. And then you can also compare how here the fluid distribution looks like that in this kind of setup. So you have a wind shadow of the mirror. So this protects more or less the fluid from hitting the sidewall, but then you have an accumulation on the A pillar of this fluid, and then from there to the side window of the passenger, not passenger, driver seat. Also, shonDye gives you the freedom, to put some sample windows in the cowl of the car. The cowl is the space between the windshield and the engine hood. So you can check how much water will go there and how much water has to be handled there. Here, as an example, after the simulation, you get 140 milliliters in the front of the car. So this has to be removed also from there. So I hope you got some deeper understanding of our products and our tools. and how to set up engineering problems with our tools. And if there are any questions, you can put them in the comments, and we will try to answer them as quick as possible and as good as possible. And yeah, thanks for your coming and watching our deep dive.
Excellent, Moritz. And with that out of the way, let's go to the questions. We have one question for you, Moritz. I think which is also an interesting one. For the wipers, how did you actually implement the periodic behavior in CSV?
We can go to where I imported. So I just said I have this already defined. And so shonDye gives you the freedom to import it by CSV. So you just need to have the definition by rods per seconds or rounds per second. So you can switch between rounds per second and rods per second. I wrote a small Python script where I think it's where I can design how fast the wipers go. So the frequency of the wipers, and also that they have a small stagnation point at the both ends of the movement. And so I wanted to mimic real behavior of a wiper. And then I wrote a small Python script and imported it as a CSV file.
Nice. What makes your method superior to other simulation methods, like classical finite volume method?
I think the finite volume method, I have always the problem if you have this kind of interaction between solid and fluid. So to define the multi-body system is everyone who did this in a finite volume CFD. It's always a little bit of a pain to define how the mesh is resolved there. You have tools how mesh is behaving, but it's never really native. I think in these particle applications like shonDye, you get this multi-body interactions in a native way, and it's not like you have to mimic the mesh and how the mesh is refined at some points, and where the mesh has to refine if you have always a moving body. So I think this is really a perfect application for this particle applications like shonDye to have this multi-body interactions and these complicated multi-body interactions like a driving car or moving of a wiper.
And one thing to mention on shonDynamics.de/case studies, you can find various use cases, other use cases. For example, the one I find the most interesting is the floating car simulation with shonDye, but also the racetrack tank sloshing, where you can actually see some real automotive application use cases that you guys can check out there, apart from other things like e-engine or navigating through puddles, car weighting, and gearbox lubrication. As we have no more questions, I would say people feel free to reach out to Moritz or the team of shonDynamics. And as I said, you can find more about them on shonDynamics.de. Moritz, again, thank you to you for the nice presentation. And if people have any questions, they can reach out to you if they want.
Thanks.
Excellent.
And bye.